It's the final countdown, guys. This is it. Welcome to the final lesson of the year. So let's get right to it. We're going to be talking about how to solve exponential equations, and these are some examples where now the exponent is the variable. Okay, so we're going to be using different properties that we spoke about before here in logarithms, right? We spoke about how logs and exponentials are inverses of each other, and we're going to be using some of those properties. So I'm going to show you two different scenarios, two different cases, and hopefully those are enough examples for you to understand what we're doing. So this first case is called common bases. This is where you have two exponent equations and they have the same base. Notice how we have 7 to the 2x plus 13, and technically here we have 7 to the 1 power. Because the bases are the same, we can then assume that the value of the exponents are also the same. Similar to logs, right? When we said that we had a log equal to another log, if the logs have the same bases, then the value inside the logs are also equal. So here, using the similar property, equality of exponential equations, we're going to just set the exponents equal to each other. We can ignore the 7s because they're the same bases. Therefore, the exponents must also be equal. And here we just solve for x. We move 13 over. We get 2x equals negative 12. Divide both sides. X equals negative 6. As always, plug it back into the original equation and verify the solution. We always want to check if we have extraneous solutions or not. So if we plug it back in, we have 7 to the 2 times negative 6 plus 13 equals 7 to the 1 power. In the top, we have 7 to the negative 12 plus 13. That's all together equals 7 to the 1 power. Negative 12 plus 13 is 1, so 7 to the 1 power equals 7 to the 1 power. We have ourselves a solution. In this next example, notice how we also have common bases, but now we have common bases on steroids. We have more bases. So what do? So let's look at the left-hand side. Notice how on the left-hand side we have this has a 3 as a base and 3 as a base. What do we know about common bases when we're dealing with exponents? I might make a little side note here to refresh your memory. What do we do when we have x to the second power times, say, x to the third power? What do we do with the exponents? Well, we're supposed to add the exponents, right? So whenever they have the same bases, we can add the exponents and just combine these as x to the fifth power, right? This is the product rule for exponents. We spoke about this a few videos back. So using the similar property here, right, we're going to add these exponents. We have this exponent and this exponent that can be added since the 3's are the same bases. Now we're only going to add the ones on the left-hand side because those are the ones being multiplied together. So on the left we have 3 to the, I'm going to write it more to the left, 3 to the negative 2x plus 1 plus the negative 2x minus 3. I'm able to combine these two into just 1 by adding the exponents. Now I'm going to combine the numerators, the common terms here. So that gives me 3 to the negative 4x minus 2 equals 3 to the negative x. I just combined the like terms, which are these right here, and then the numbers are also like terms, and that's how I got that negative 2. So now that I have the same bases, and I only have one on each side, I do like I did in the previous example. the exponents must be equal. So I solve negative 4x minus 2 equals negative x. Move the x to the other side. Negative 2 equals 3x. Divide both by 3. X equals negative 2/3. Now, again, we have to plug everything back in and check that the solution works. I'm not going to do that to save time on this last video, but if you plug it back in, you just have to multiply some fractions with some numbers, and when you combine them, you'll know that they're actually equal to each other. All right, next scenario. Here we're still dealing with common bases. Now notice that this 5 and the 125 don't look similar at first, but I can always change a number to an exponent if I know how to manipulate it. Now I know that this right here is also expressed as 5 to the third power, because 5 times 5 is 25, and 25 times 5 is 125. So my first goal when I see exponential problems that have different bases is, can I convert one of them to make it look like the other one? Can I make them common when they don't look common? And in this scenario, we can. So we have 5 to the 2x minus 11 equals 5 to the third. Now that I've manipulated and have common bases, I can ignore the basis and just write the problem as the exponent. 2x minus 11 must equal to 3. And we continue to solve. Plus 11, 2x equals 14 divided by 2, x equals 7. And if you plug this back in, it should also work. This is what I like so much about math, is that something that can seem at first very complex, right? Something like this, that you're like, how do I do that now? I can manipulate any number and change it to another equal value so that I can use the properties that I know to continue solving. So what do we do when they don't have common bases, where you cannot make common bases? Here are some scenarios. Before we talk about examples on how to solve problems that have different bases, let's just talk about the second case. It's called using inverses. So let's review a little bit. An inverse is when two things are reciprocal of each other, or they cancel each other out, or we use them to solve, right? We usually use the inverses for, like, say we have x squared equals 9. How do we solve for x? Well, we take the square root and the square root of both sides, because the square root is the inverse of squared, so it just results with just x equals 3. Positive or negative 3, of course. If we did, let's see, 2 times x equals 8, well, here we're multiplying 2 times x, so the inverse is to divide, and x equals 4, right? We've been using inverses all year long with square roots, with squares, with all of these different types of equations. Well, now we're going to do that with exponential functions or exponential equations. So let's talk about some common inverses. If we think back to the definition of a inverse, let me erase some or make some space here. Right, when we spoke about logs, how to convert one log to another, we spoke about using the definition of a logarithm is that you move the base to the other side and you can cancel things out. Okay, so this is what I mean. If we have the log base b of, say, y equals x, we can convert this log to its exponential form by moving this b over. The log cancels and you're left with y equals b to the x. Technically, because these two have the same basis, log b of this function, let's call it, of this function, should be the inverse of b to whatever function you're dealing with. Those two will always be inverses of each other. Okay? So if you're dealing with, let's say, 5 to the x or e to the x, or really anything, you can always take the same base and think of that as the inverse function. Here's what I mean. So let's say we have 10 to the x. What is the inverse of 10 to the x? Well, the inverse is going to be log base 10 of x. What is the inverse of e to the x? We said it was log, well, in this scenario, it's log base e. Log base e of x. Or just natural log of x. Now, how is this helpful? Well, let's say that we have some problem. We can also do this with, say, any number. I'll show you in a little bit. Let's say that we're doing 10 to the x. If I take the log, or the inverse, if I take this same part and I take the inverse of this, kind of like when we did x squared equals 4, we took the square root of both sides, right? If we square root, this cancels. Well, if we take the log base 10 of this piece, what's going to happen is we're actually going to be able to use the log rules to move this to the front by using the power rule. This allows us to say x times log base 10 of 10. Right? The power rule allows you to move the exponent to the front. Now, because these are inverses, log base 10 and 10, because we have the same number here and here, this is always going to cancel n equal to 1. So it's just going to give us the letter x. Same thing with this over here with the e to the x, or any number really, 5 to the x. If we take the log base 5, the inverse of it, of this piece, the x is going to go forward, and the log base 5 of 5 is going to just equal to 1, and it'll cancel out. This is the method we're going to be using for the next scenario, where we talk about use the inverse, is use that common base to cancel things each other out. Just like we did the inverse of squaring, we took the square root of both sides, we're going to do the exact same thing, but with logs and exponentials. So, here's an example. Let's say that you don't recognize this as common bases. Let's say that you don't know that this 16 could be rewritten as 2 to the 4th power. If you did know, then we use the first case where the 2's are the same and then just x equals 4. Right? But I want to use a simple example like this one to show you how would you do this using logs or inverses to solve for an exponential equation. I know that the answer is going to be x equals 4. Right? 2 times 2 times 2 times 2 equals 16. Now, let's say that you didn't know any of this. Let's say that you couldn't recognize these as common bases, and you're like, oh, how do I do it now? This is where we use inverses. So I'm going to show you 3 different methods on how to solve it. I'm going to call it method A, B, and C. So, for method A, I'm going to take the inverse of whatever base I see here. So I have 2 to the x, which means the inverse is log base 2. Now I'm going to take the log base 2 of the left and log base 2 of the right. What happens here is that now, I'm going to make some space. I'm going to take the exponent and move it to the front. So I have x times log base 2 of 2 equals log base 2 of 16. Now, log base 2 of 2, because they're the same or because they're inverses, right, this is always going to cancel to 1. So I can just cancel the left, leaving me with x equals log base 2 of 16. Now, in your calculator, if we were at school, or if you have a TI-89, 84, Inspire, any of those types of calculators, you should be able to find a button with logs that has a little square down here where you can input this 2. Okay, now, because we don't have, I'm assuming you don't have a Inspire, an 84, or an 89, or any of those kind of TI calculators, we're not going to use this method. We're going to use the natural log method or the log method to solve, because these two options you do have on your cell phone. If you tilt your cell phone sideways, you get more options where you can see the log, the square root, the natural log exponents, all those kinds of things. So for these two methods, I just want to expose you how this would work, right? This solution would actually result in, when you put it in your calculator, when you change that base, you would get x equals 4. Okay? Of course, you want to plug this back in, solve for x, blah, 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 and see if it works. I'm going to show you these two other methods. This is method A. Method A we will not use for this assignment at all unless you have a calculator, right, that has this capability of changing this base. We're going to stick to the ones that you should have on your phone, which has base 10 and base E, which is your natural log and your log. So let's do it this other method, method B and C. I'll change colors here just in case things get a little bit crazy and overlapping. Okay, so method B. I'm going to take just the log of both sides. Log is technically an inverse of an exponential, so it doesn't really matter what type of log you take. As long as you take the log of an exponential function, they're considered inverses. So if I take the log of the left and the log of the right, technically this is base 10, we can still use the power rule, where we can bring this exponential function, right, or this exponent to the front. The power rule works anytime you have a log. So if I move it to the front, I have x times log of 2 equals log of 16. Now, to solve for x, since we're multiplying here, the inverse is to divide both sides by log of 2. And we result with x equals log of 16 divided by log of 2. Log of 16 is some sort of decimal. Log of 2 is also some sort of decimal. When you divide them, you should get x equals 4 as well. I wouldn't round at all when you're plugging the log. I would just leave it, if you can, entirely like this, divided by this. And you should get a 4. Now, what's the third method? Third method is part C. It's really the same thing, but instead of using log, we're going to use natural log. So I'm going to substitute, instead of taking the log of both sides, I'm going to take the natural log of both sides, because natural log is also a similar type of log. I'm going to minimize this, make some space. So natural log, as I was saying, is really just log base E. So I can also take the natural log of both sides. And this is how it would work. Let's do this let's keep it in black. So if I take the natural log of the left and the natural log of the right, I can still use the power rule where I'm allowed to move the exponent to the front, right? A natural log is still a log, so the power rule still works. So I have x times the natural log of 2 equals the natural log of 16. Similarly, since we're multiplying, we divide both sides by natural log of 2. And you're left with x equals the natural log of 16 divided by the natural log of 2. And when you put that in your calculator, you get different numbers, because now you're using log base E versus log base 10 as we did over here, right? So you're going to get this ratio and this ratio are not going to match as this ratio over here. Sorry. These numbers are not going to match these numbers, but the ratio should still be the same. When you divide those two numerators and denominators, you should still get x equals 4. So for this assignment, when you're dealing with inverses, you want to use on your phone log or natural log. They look exactly the same, except that one of them is in base 10 and one of them is in base E. Okay, this is basically it. I'm going to show you a few more examples on how to solve more complex ones here in a minute. So stick around. Again, I'm not going to focus on this method, right? I'm going to focus on method B and method C. Okay, so notice how we have an exponential equation because x is an exponent, and here we don't have any possible way of making these common bases. I cannot change a 7 into a 3 to some power, right? 3 to some power should give me 7. It's a little bit more complex than that. So because we cannot think of that easily, we're going to use the inverse method. I meant to not write all methods. I'm just going to write inverses. Okay, so here we're going to take the, let's go with log of both sides, right? It honestly doesn't matter how you do it. Let's take the log of both sides, or natural log, whatever you prefer. I'm going to take the log on the left of 3 to the x equals the log of the right. As long as you do it to both sides, it should be balanced and it should be okay. I'm going to take the power rule every single time and move that to the bottom. This is really the only reason why I'm introducing a log into the function. I cannot solve for x when it's in the exponent, but I can solve for x when it's in the bottom. So by introducing the log on both sides, I'm able to manipulate the exponent and bring it down to the bottom. X times log of 3 equals log of 7. To solve for x, I'm going to divide both sides by log of 3 because I want to isolate the variable. These cancel, and you're just left with x equals log of 7 divided by log of 3. When you put in your calculator, you should get some sort of decimal, 1.771. Now, we're going to be rounding to the nearest thousandths of a decimal, which is 3 decimal places, right? Anything less than that, it'll be less accurate. I would go with as high as many decimals as possible, but 3 should be enough to solve it. Now, for this scenario, I'm going to show you how to plug it back in and solve it, right? Plug it back into the original equation and see how it's the same thing. This can also be done in your calculator / your phone, but you always want to be able to plug it in here and say 3 to the 1.771 power. Does this equal 7? Well, when you plug it back in, you get 6.998. And because we rounded over here, then it's okay to assume that we're able to round over here as well. Rounding very, very small numbers to make them equal is okay. If you're rounding a 6.4 to make it look like a 7, that's way too much rounding. Rounding should be minimal, which is why we want to use as many decimal places as possible in our solution, but 3 should suffice. All right, next example. Here I have the natural, I have e as the base, so I'm going to want to use natural log, right? Again, I'll show you how to do both of these with I'll show you how to do it with log and natural log. Let's start with natural log. So first, I need to leave the exponent part by itself. So I need to move the 5, and I need to move anything attached to this piece right here. Move everything to the other side. So I'm going to subtract 5 on both sides. I'm going to rewrite it over here so you can see the scenario. 5 plus e to the x plus 2 equals 21. So subtract 5 on both sides. I get e to the x plus 2. Technically, all of this is together. You can put parentheses if you prefer. Equals 21 minus 5 is 16. Here, I'm going to take the natural log, which is also known as log base e, right? Natural log is the same thing as saying log base e. So, if I take the natural log on the left, and the natural log on the right, I can bring this exponent to the front. This whole thing will go to the front, and you're left with x plus 2 times natural log of e equals natural log of 16. Remember that natural log is log base e, which means this should cancel each other out, right? Remember when the logs have the same bases, log base e of e, this always going to cancel each other out because the base and the exponent as the base will always equal to 1. So as long as you remember that this statement log base e of e is equivalent to natural log of e, then you will know that those two will always cancel each other out. Okay, so what am I left with? I'm left with x plus 2 on the left equals natural log of 16. So x plus 2 equals, since this canceled out, this is equal to 1, equals the natural log of 16. At this point, I would put this in the calculator, or if you want, you can subtract 2 on both sides, and then just have, let's make this a little smaller. X equals natural log of 16, which is some sort of decimal, subtract 2, and you get x equals 0.773. Now, I'm not gonna check for extraneous solutions. You can plug it back in, and you can check for extraneous solutions. You should always check if it's true or not. I'm gonna show you the same scenario but using logs. And then you can choose for yourself if you prefer using natural log or log. It doesn't really matter. It's very similar pretty much the entire way. Okay, so I'm going to do the same problem but using logs. I have 5 plus e to the x plus 2 equals 21. Subtract the 5 on both sides. E to the x plus 2 equals 16. Take the log of both sides. So I want to make some space actually. I'm going to take the log on the left and then the log on the right. On the left, I can bring the exponent to the bottom as x plus 2 times log of e equals log of 16. Now here, notice how this is base 10 and these are not the same bases, so this is not going to cancel each other out. So the difference between this method with natural log, because we use the e, and this one that is not inverse, you would just have to divide both sides. So since we're multiplying, we divide both sides by log of e. Log of e. E is just a constant. It's a number, kind of like pi, 3.14, right? E is 2.71, dot, 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 dot. It's another constant like pi. When you divide on the left, these cancel out, and you're left with x plus 2 equals, this goes in your calculator, log 16 divided by log of e. When you divide those, you get 2.773. When you subtract 2 on both sides, you get x equals 0.773, which is the same thing as over here, right? The reason why I would naturally go, no pun intended, with ln or natural log on this scenario is because e is the inverse of natural log, and it's going to cancel nicely over here. But if you do the log, it doesn't really matter. You'll just have to divide it on both sides, and you'll have to put this in the calculator. You'll end up with the same result. So moving forward in this last example, you can use log or natural log. Ideally, use the one that's exactly the inverse of the base that you're dealing with, but if not, just use log and natural log. You're still going to have to use your calculator regardless, so it doesn't really matter. Last scenario. So here I'm going to move the 3 over. I have 5 to the 2x equals 12 plus 3 is 15. These two bases are not the same, and there's no way to make them the same. So I'm going to take let's go with natural log. Okay, let's go with the natural log of both sides. When you take the natural log, let's put 15 here. When I take the natural log on the left and the natural log on the right, I can bring the exponent down, right? I cannot do this method without doing the previous method first. This has to go away. I need to have this exponent by itself so that when I bring it to the front, there's nothing attached to it, right? So that's the most important step. When you have many things going on here, make sure that this part is completely isolated. So move everything over, use PEMDAS, use all that stuff, right? Move it across, divide, do the opposite. Once it's by itself, then you can bring the exponent down by using the natural log properties. So this is what I'm left with. I'm left with 2x times the natural log of 5 equals a natural log of 15. I divide both sides by natural log of 5 because I'm still trying to isolate the variable. I'm left with 2x equals the natural log of 15 divided by the natural log of 5. Now, when you put this in the calculator, you should get 1.683. So 2x equals 1.683. Quick side note, I want to make sure that I clarify that these two, you cannot assume that this is the same. You can't just say, oh, well, why can't I just cancel out the 15 and the 5 and say this is the natural log of 3? And the answer is no. Why? Because if you remember the property rules of logs, when you're dividing natural logs, right? 15 divided by 3, this is the same thing as saying natural log of 15 minus the natural log of 3, right? This is the quotient rule. Notice how we're subtracting them, and here we're dividing them. We're not subtracting them. So you cannot say that the natural log of 15 and 5, these just cancel out to give you 3. You cannot do that. You have to put them separately on the calculator and get this decimal 1.683. Once you have that decimal, then divide both sides by 2. I'm going to continue solving this over here. 2x equals 1.683. Divide both sides by 2. X equals 0.84 or 0.85, depending on how you round and stuff. And of course, you always want to plug your answer back in, check for extraneous solutions, but this one should actually work out. I checked it myself. I hope this answers your questions. I know this is a lot to cover. If you have any questions, just let me know. Send me a message and remind, and we can talk about more of this on Zoom. Normally, we would spend at least a week on this topic. So I try to do as many examples as possible so you can see more scenarios. But feel free to send me a message and we can chat more about how this works and different ideas and stuff. Yeah, guys, this is the last lesson. So I hope I was helpful to you, and that I made this experience as best as possible, at least in mathematics. I understand there's going to be a lot of gaps next year into the next math subject that you have, because learning everything through the internet is not possible, right? Even if you did your best, doesn't mean you learned everything. There's a lot of little gaps that I had to take out to make sure that we covered all the material. So feel free to come back to me next year and talk to me about whatever problems you have in math. I feel like very responsible for your education while you're learning online, and if you have gaps next year and things that you don't understand because you should have learned it through online, then it's completely on me. So I hope that the videos that I made were helpful and useful, and if they weren't, just come back to me, not at me. Come back to me and I'll help you out, and I'll always clarify stuff. All right, guys. Calculator.